every regular language must satisfy the pumping lemma. So in this case, we have already seen in case of the finite automaton, we have the FA, and we know that in your FA we have the finite number of states, and that's why actually this is called the finite automaton also. So we have the finite number of states, and you have seen that some regular language may have many possible strings of any possible lengths. So your string length may be 0 or 1 or 2 or 3 or 4 or any length. Your string can be of any length, but if the language is regular, then whatever be the length of the string, irrespective of that, you will be able to recognize the sentence of the regular language within the finite number of states. So you must have the finite number of states, even the length of strings may be very large. So how this is possible, actually we need to see. So see, if you have the finite automaton, so assuming that M is the FA, where Q, you know that this is the set of states, sigma is the inputs set, Q0 initial state from where your finite automaton start, A is the set of accepting states, and delta is the transition function. So here what we assume that the Q is finite set. Q has finite number of elements, and suppose you can say the cardinality of the Q, is equal to n. N is some integer. Okay. So n can be 1, 2, 3, 4, 5, 6, 7. You may have only one state of the FA, 2, 3, 4, 5, 6. So Q, cardinality of Q is n. So if you have some language and which is accepted by this machine, you can say let L is one language which is accepted by the machine M. So you can say language accepted by the M is equal to what? L. So assuming that L is the language which is accepted by the FAM, or you can say L is recognized by the machine M. Okay, and let us take some X which is in the sigma star you have, and we assume that the length of X, you have some string and the length of the string can be anything. So we assume that length of X is more than or equal to n. So we have the string X whose length is at least n. And what is the condition? We see that let this X belongs to the language. Okay. So we have seen you have the FA where we have the finite number of states. We have seen that n is some positive number and some integer. The cardinality of Q is some n. We don't know what is exactly n, but we assume that there is some integer n, and the number of elements in the state of the FA is n. Language accepted by this machine is L. We have taken one string X from the sigma star, and we assume that length of X is more than or equal to n. And also we see that we assume that X belongs to the language. So see, we have the n number of states, and your string length is what? N. So for the simplicity, you can say X can be written like this. How you can write? X can be say A1, A2, A3, or AN, Y, where you can say A1, A2, A3, AN, all such belongs to sigma. We assume that these are some symbols from the sigma, and Y belongs to sigma star. So Y can be empty also, because we have assumed that the length of X is more than or equal to n. So if length of X is more than or equal to n, we can write like this. X can be written like A1, A2, A3 up to AN, A1 is the some input from the sigma, some input symbol from the sigma. A3 is some input symbol from the sigma. An is also some input symbol from the sigma. And y is the remaining strings. If length is more than n, then y is the remaining some strings. So this is we assume. So see how your FA is going to accept, how once it reads the string x and how it is going to accept. And we know that if you have the transition function is delta star, and if you are at the state q0, q0 is initial state you have, and if you are at the initial state and your FA is going to read the first symbol, say a1, you have the a1. Or if you are given x is the string, so at the state q0 we have some null string. Okay, you have null string. So where we go in case of the FA, you know that from, if this is the finite automaton or DFA, then if you, from any state, if you have the null string, then your FA is remain in the same place. So your FA will be in the q0. So this is actually equal to what? q0. So this output of this transition function is what? The state q0. Now see, one by one you are now consuming the input. So you are in the state q0 and now you have the to read the string. I'm talking about the delta star. Okay, so this is not the normal transition, extended transition delta star. So you consider this as the string and this as the string. So now you have the substring. You are supposed to consume the x. A1 is the substring. So how would you know where you can go? Assuming that your machine goes to some state on reading this input. For reading the null string from the q0, we know that it remains in the same place q0. When you are at the q0 and depends on the input symbol, your machine may go to some state. Okay, so assume that your machine goes to the state, say q1. Next, you can say if you are at q0 and you have given the string a1, a2. So once you have consumed a1, you are in the, up to this string, you are in the state q1. From that state, if you take the other symbols, say a2, you will go to some state, assuming that you are going to the state q2. Similarly, if you have delta star, q0, a1, a2 and a3. So on consuming this substring a1, a2 and a3, where your FA can go? Your FA can go to the state. We assume that you have some state where your FA can go. Now we have the situation like this, and you can go up to the, you are at the state q0 and you are given the string a1, a2, a3 and then an. So for accepting the first symbol a1, assuming that your machine goes to the a1, for q2 your machine goes to the q2, for up to a3, a1, a2, a3 your machine goes to q3, up to the substring a1, a2, a3 up to an, assuming that your machine goes to the state q1. So you have read till now n symbol of the string. You have the string x and you know that this string is in the language. We have assumed that x belongs to the language and the length of x is more than or equal to n, means y can be null also. So you have read up to a1, a2, a3 and an, and your machine goes to q1. If every state q0, q1, q2, q3, qn are distinct, then how many such states are there? Reading up to the string a1, a2, a3 and an. And if every time for consuming next symbol, if machine goes to the different states, means if every states are distinct, if they are distinct, then you have how many states? You have total n plus 1 state. So Q0, Q1, Q2, Q3 up to Qn. So n plus 1 states you have, but you have already assumed that you have the machine where the cardinality of Q is n. So what this says that there must be some state which repeats at least twice. Okay, so by the principle, pigeonhole principle, by the pigeonhole principle, there must be some state. So if you have the number of state is n, and if every time if you are going to the new state, then you have the n plus 1 state you need actually, but you have assumed that your machine has n number of states. So there must be some state that is going to repeat. Means you may say that Q1 can be same as Q2, or Q1 can be equal to Q3, or Q1 can be equal to Q1, or Q3 can be equal to Q1, or Q0 can be equal to Q3, whatever. So there must be some state must repeat at least twice by the pigeonhole principle. So pigeonhole principle says that you have more, if you have the less number of holes, say you have the 2 holes and you have the 3 pigeons, you have 3 pigeons, then there must be some hole that contains more than 1 pigeon. So if you have the n number of states, and if you think that every state is distinct, then you need actually n plus 1 state, and that's why we say that out of these n plus 1 state, there must be some state which repeats at least twice. And this is the way you are saying that, but you don't know which states is going to repeat at least twice. Assume that let qi can be equal to qi plus p, where I can we start from what? I can we start from the 0. So q0 can be equal to I plus p. So we have the condition actually. You have I can be greater than or equal to 0. I must be greater than or equal to 0, and I must be less than I plus p. Why I plus p? Because I'm saying that there must be there must be some state that repeats twice. Means qi is equal to qi plus p. So the p should be greater than, means p should be greater than 0. That's why if I is 0, then p can be at least 1. Means if I is 0 and p is 1, means you are saying that q0 and q1 states are same. Where so you can have I can be anything, I can be 1 also, I plus p can be either 2, 3 or up to n. If I is 0, then your I plus p can be either q1, q2, q3 or q1. Maximum is what? N. So this I plus p should itself be less than or equal to n. So you have the n plus 1 states, and n plus out of n plus 1 state, there must be some state which is going to repeat at least twice. So we assume that qi is equal to qi plus p, and this is the condition. I plus p must be greater than greater than I, means you must have I plus p must be greater than I, means you are talking about p cannot be equal to 0, because I can be 0 also. So this means you can say you are at the state q0, you are at the state q0, and from q0 you are reading the string, and we are assuming that you are going to the state qi, and then this is the final state, say this is the qf, this is the final state. Okay, you are at some state, say for example you are at the q0, and you are reading the input strings, and on reading the input strings you are visiting some states. Okay, you are visiting some state, we don't know, but finally you are going to the state qi. For what strings you are going to the state qi? you are going to the state qi. For the substrings, you have the a1, a2, a3 up to ai, which we assume as u. So we have assumed that u is equal to a1, a2, a3 up to ai. So your fa is going to some states, and finally after consuming this substrings u, it is going to the state qi. Now from this it has to read the input. From the state qi it has to read the input and say it come back to the same place. For what string it come back to the same place? We have the strings like you have the string ai plus 1, ai plus 2, and then ai plus p. This is the string v. So for the strings v, you are in the same place. Here you can visit number of states. We don't know which states you are going to visit, but you come back to the qi. This is the condition. Now from qi you can have some remaining part. You have some remaining part, and this is the string w. What is w? You have ai plus p plus 1, ai plus p plus 2, then you have the an, then you have the remaining string. So ai p plus 1 to ai p plus 2 to ai means this is the remaining string. On reading the remaining strings, your fa goes to the final state. Now this is the way you can say that this is the first loop comes. Means here starting from the q0, if you have the strings whose length is more than or equal to n, where n is what? Cardinality of states is n. You have the n number of states, and you have the string whose length is more than n. Then we have seen that there must be, if you are accepting, if x belongs to the language, then there must be some state which repeats at least twice. And this is the first loop encounter. This is the loop you have. So what you can say means you can say that if you are at the state q0 and you have the string u, you are going to the state qi. Whenever you are at the state qi and you are given the next substrings, say v, this is v, then you are going to the state qi, and you have the remaining substrings. You are at the state qi, and once you are given the remaining substring w, means you are going to the state qf, which belongs to the final state. This is. So you have seen. So what you have seen here, since your x belongs to the language and you have the x here, we have decomposed the x actually in three parts here, u, v, and w. So x you have decomposed into the three substrings u, v, and w. So on receiving u, your fa goes to the qi. From once you are at the qi and you are receiving the next substring v, you are going again to the coming back to the qi. From qi, if you receive the w, you are going to the point state. So where you know that v, the length of v is greater than 0. You must have at least one element here. That's why you have the loop comes. So this says what? This says, you can say in this way, you can say you have delta star. If you are starting from the q0, then u, v raised power m and w, all such strings belongs to the, for all such strings your fa must also go to the final state. and QF. Why it is so? For for every m, which for every m greater than or equal to 0. See, why it is so? If if m is equal to 0, if m is 0 means you have x is equal to, you are given the string uvw, and we say that all such strings, for reading you are going to the qi. From qi, if you are supplied the v, you are again coming back to the qi. From the qi, if you are given w, then you are going to the qf. This means if you have uvmw, okay, and if you have m is equal to 0, then if m is 0 means this is you don't have the v here now, so you have the string uw. So question is that whether uw belongs to the language or not. Of course, this is because on receiving the u, your fa goes to the qi. From qi, if you supply the string w, for w you know that your fa goes to the final state. So this must also be the final state. So in addition to this, we are given that this is the x which is in the language. So with this kind of notions, when you have the finite n number of state and the length of the string x is more than n, then you have some state which is going to repeat at least twice. So this is the loop comes, and if m is 0, then if you discard this part, then uv will also be in the language. Also, if v is equal to 2, so uv and 2m, so uv2w, this also belongs to the L. Why it is so? Because for you are coming to the qi. From qi, you have the v, means v and v. So you have the v. For the v, substring v, you are executing and coming back to the qi. Again, you have the same substring v. So again, you are going to this case. Then from that qi, you have the w, and you are going to the final state. So that's why this is known as the pumping lemma, because you have the loop comes and you are pumping, you are given one strings whose length is more than the number of states in your DFA, and in this way you have some loops comes, and means if you can repeat the loops, then all such strings will also be in the language. In addition to the strings uvw, you can also find more number of strings that can also be in the language. So you say that all such strings uvmw, for every m greater than or equal to 0, for which your fa goes to the final state, and hence all such strings are also in the language. So simple condition is that you are at the q0, and for the string you are coming for the strings you are coming to the state qi. From qi, you have the v, and you are going to come back again. Again, if you have v, again you can go to this part. Again, if you have v, again you can repeat. Again, if you have the v, you can also repeat. Again, any number of times you can repeat, any number of times. And finally, for the case of w, you reach to this place. And all such strings which you are going to repeat here, all such strings are in the language. So this is actually the pumping lemma, which says that if you have the string whose length is more than the number of states in your DFA, then there must be some loop comes, and it means that on knowing only one string which is in the language whose length is more than n, you can pump up more number of strings that are also in the language. So in this way, all such strings uvm, for every m greater than or equal to 0, all such strings will also be in the language. Means you can say that uv M, W, all such strings belongs to the language. And L is what? L is the language accepted by your machine MA. And for every M greater than or equal to 0. In this construction, you come to know that if you have the n number of states in your DFA and your string length has more than n, then you have some state that repeats at least twice, and you form a loop. See, once you are at the remaining part, say for example W, for remaining part you may also, if from W can length can also be more than n, there is no problem. You may also have some loop here. But what we have just encountered the first loop, and we say that okay, on behalf of the first loop itself, we can pump more number of strings. So here also you may have loop. We don't worry about this. We have just find the first loop occurs, and means you can pump more number of strings that are also in the language. So this says that if UVW, if X is in the language, if X is in the language, and you have the condition like you have for the U you are going to the QI, and from QI if you have the V you are coming back to the QI, and you know that I plus P can be what? I can plus P can be less than or equal to N, means the length of UV can be less than or equal to N, and V is what? We have assumed that V is greater than 0, means you must have some element, means you must have some, it should not be 0, that's why loop comes. So number of elements in the substrings V must be at least 1, that's why you have the loop comes. So okay, so this says that if you have the condition like this, and then what we have for any M greater than or equal to 0, you have U, V, M, W. We have the X, you know that we have the X which is U, V and W. So UV length is less than or equal to N. V you know that must be greater than 0. So for any M greater than or equal to 0, U, V, M, W will belongs to the language with this construction, because this is the V, this is the string V, and for V you have the loops, and any number of times if you can repeat, you have any number of times, then you will get the some different strings. Okay, so now we will see, this is the base of your pumping lemma. So now we see the pumping lemma for the language. So actually this is the known as pumping lemma that we have already described informally. So it says that suppose L is a regular language. We assume that L is a regular language. Then there is an integer n, so that any x which belongs to the language, any x which is in the language with length of x is more than or equal to n. Actually this n is the number of states we have already seen in construction. So there must be x, we have taken the x whose length is more than n. There are strings u, v and w, so that x can be written as u, v and w. So we have the strings u, v and w, so that you can write like this, with condition that length of, okay, you have the length of uv, so length of uv must be less than or equal to n, and length of v, we know that length cannot be 0, so you must have at least one symbol, and we have seen that for any m greater than or equal to 0, u, v, m, w belongs to the language. So this lemma says that if L is the regular language, then you must have some integer n, and if you have some string x which is in the language, and if you can take the x whose length is more than at least equal to the n, so that you can write x in 3 substrings u, v and w with the condition that length of uv is less than or equal to n and v is greater than 0, then for any m greater than or equal to 0, you have the string uvmw belongs to the language, and v is cast the loop. This is the loop. So if L is regular language, then this must satisfy the pumping lemma. So this is one way to prove that if you are given some language and you are asked that whether the given language is regular or not. For example, if somebody says that if you are given the language L, so you can say 0 I 1 raised power I, such that I can be greater than or equal to 0, no problem. So you are given the language L, which is 0 I 1 I, means same number of 0, same number of 1, and all 0 must come before the number of 1s. So ith number of zeros and ith number of 1s you have, where I can be greater than or equal to 0. And somebody may ask you that, can you prove that, can you construct the FA for this language? So if you can construct the FA, finite automaton, for this language if L is regular. So how would you prove that L is regular? So for proving this, we have seen number of ways. One way is to, you can go for the regular expression for this language. If the regular expression, if you are able to obtain the regular expression, then you can say that yes, the language is regular. Other ways, you can go for the regular grammar. If you have obtained the regular grammar, then you can say that yes, the language is regular. Other way to prove that whether L is regular or not, what you need to do, you can compute the number of equivalence classes. And if number of equivalence classes are finite, then there is a way to construct the finite automata with finite number of states. Means you have the FA with finite number of states, and hence the language is regular. So and other way is to directly construct the FA. Now this is one of the also possible ways. You can use the pumping lemma for proving that whether the given language is regular or not. If the language is regular, then it must hold the pumping lemma. So how can you prove that the language is regular? So if this is regular, then this must hold the pumping lemma. It means you can construct the FA recognizing this language with finite number of states, with assuming that n number of states you can have. So for proving that whether the language is regular or not with the help of the pumping lemma, you can assume that the language at the beginning, you can assume that language is regular. And if it is regular, then it must hold the pumping lemma. Then try to apply the pumping lemma. And if you achieve some contradiction, then you can say that, okay, yes, earlier assumptions that L is regular is not true, and the given language is not regular. So actually, if you want to disprove that, okay, this is not the regular language, then you must have some contradiction achieved. So at the beginning, while proving, we assume that you have to assume that L is regular. L is regular. So we are going to assume that L is regular. So we need to prove. Okay, you have to prove it. So prove whether or not L is regular. L is regular language. So we need to prove this. So for the step says that you can assume. We assume that the language L is regular. If the L is regular, then it must hold the pumping lemma. It means you have to select some strings from the given language, and you have to ensure that the length of the strings must be more than or equal to n. This is assumption, but as actually we don't know what is exactly n. So in your selection, you must involve the n, so that you come to know that okay, yes, the string length is at least n. So right, like you can say, let x is equal to 0 and 1n. So see, we have taken the strings, one string 0 and 1n, and this we know that this is in the language, because this is the 0 I, 1 I greater than or equal to 0. All such strings are in the language. So we have taken one such strings 0 and n number of zeros, n number of ones. So this is in the language. And also, since we know that pumping lemma says that if L is regular, then there is an integer n. And we have taken the string that belongs to the language whose length is at least n. That's why it is better, it is good idea to include n in your selection, because we don't know what is n here. So you can take any strings, any simplest string for which you can easily achieve the contradiction. So this we have taken 0n, 1n, and this is in the language, and we are sure that the length of x is more than n. So we have the condition that x must be greater than or equal to n. Now you know that u and v, we don't know what u and v are. We don't know the substrings u and v exactly, but we can assume that since you have 0 power n, means n number of zeros, and the length of uv is less than or equal to n, this means you have some uv can be some zeros, the uv can be some zeros, let 0 power k for some k, for some k. So you have some string of uv is actually the strings of zeros, because maximum uv length of uv is less than or equal to n, and you have the n number of zeros. So k can be less than n or equal to n, no issue. So we have assumed that what exactly u and v are, we don't know, but you can assume that since we know that length of uv is less than n, and you have the n zeros, it means you have some zeros. uv is the string of some zeros. So for some k you have, and we know that v is what? V also, since v includes in this string, so v will have some zeros, and assuming that there is j number of zeros, and you know that length of v is more than 0, it means the j cannot be 0. J should be greater than 0. So for j greater than 0, j cannot be 0, because we have the length of v is more than 0. This theorem says. Okay. So now this is the way you can assume somewhat u, v, because we don't know exactly what u and v are there. So with the selection of your strings, you come to know that okay, some zeros are in uv, and since length of v cannot be 0, you must have at least single 0. So that's why v can be a string of some zeros. Here j can be greater than 0, and j can be j can go through up to k. So if j is equal to k, then you have the length of u is null. U will be null. Now, pumping lemma says that if this is the regularly, you have assumed that you have assumed that L is regular, and for that you have selected the string x whose length is more than n, and you have come to know that there are some zeros in uv and there are some zeros in v. So if this is in the regular language, then all such strings uv and w should be in the language. So uvm You can write what u v m is there. U, so you don't know u, what is u, but you know that we have uv, so you can say uv, you can divide like this uv, then you have the v and m minus 1, because you have used 1v here, so and you have the remaining substring w. Now uv we have assumed that some case, so 0k is the uv, then v is 0j, okay, and then if you have 0 power j, this is the v, then you have power is m minus 1, and w is what? W is the remaining substring. So what are the remaining? You have uv contains k number of zeros, k can be at most n, so remaining strings can be like 0 power, since you have the n number of zeros, so n minus k. You may have some, if k is less than n, then you will have some remaining zeros here, and you have the n number of n ones. So this is the remaining substring, this is the w, you have, this is the w, okay, this is the w. Now what you can see? You can see here, if you simplify here, 0 power k and 0 power n minus k, so k cancel, and you have actually n, 0 power n, 0 power n, okay, you have 0 power n, and also you have this, so 0 power n from here, and plus what? J m minus 1, because here you have 0 raised power j m minus 1. So this and this, it comes out n plus, because k and k cancel, so n plus j m minus 1, okay, and now how many ones? You have the n number of ones. Now see, this is you have obtained by applying the pumping lemma, and if m is equal to 1, if m is equal to 1, then what happen? Then this will be what? So you will have, if m is equal to 1, then see, you have m is equal to 1 means this part is 0, so you have 0 n zeros and 1 n number of ones, and since same number of zeros and same number of ones, this belongs to the language. Yes. Now this should not be satisfied only for one cases, it can hold for every m, for every m greater than or equal to 0. So if you take even 0, if m is equal to 0, m is equal to 0, then see what happens. If m is equal to 0, then minus j, and you know that j is greater than 0, it means some less number of zeros are here. So you have 0 n minus j. If m is 0, then you have minus j here, so n minus j and 1 power n. This means j is more than 0, j cannot be 0. This means you have some less number of zeros as compared with 1, and hence this is not in the language. If you take m is equal to 2, then here 2 minus 1 means j. So again you are going to take n plus n plus j. So m is equal to 2 minus 1, so j it remains, and you have 1 power n. It means you have n, j cannot be 0, j is more than 0. It means you have more number of zeros and more number of zeros as compared with n, and hence clearly this is not in the language. And this is the contradiction we have achieved. This is the contradiction. Okay. So the contradiction in the assumption that L is regular. So you have assumed that L is regular, but if you assume L is regular, then this is the contradiction you have achieved. If M is regular, if the language is regular, then it must hold the pumping lemma. But you see that it is satisfied only for M is equal to 1. If M is equal to 1, then only it is in the language. But for all other cases except 1, this is not in the language. And hence you can say that your assumption was wrong, that L is regular, and this proves this proves that L is not regular. So here you have, so by using the pumping lemma, you have proved that the given language is not regular. So applying the pumping lemma is very simple. So if you are given some language, then you just let that, okay, the given language is regular, and try to find out some strings, easiest string which includes the n, so that you at least you can ensure that the length of the chosen string is more than or equal to n, that is in the language, and then you can easily identify u, v and v, so that you will be able to achieve some kind of contradiction. And once you achieve the contradiction, then it says that the given language is not regular. The assumption you have made that L is regular is wrong. So this is the biggest question actually, how to choose the X. So we don't require, if you have chosen at least one such X for which you have achieved the contradiction, then you don't require to prove for any other strings that is in the language. So you just find at least one such string, simplest string for which you can easily achieve the contradiction. See, let us see some different language. If you have the language, say, if you have the language L, which says that, which is which contains the strings belongs to 0, 1 clean star, such that X contains equal number of zeros and ones. So this is the language. If you are given the language like this, and which says that you have the language which says L is the set of string X which is taken from the 0, 1 clean star, such that length of X means length can be anything, but condition is that X contains equal number of zeros and ones, the same number of zeros and same number of ones. So you can see the strings in this language can be what? Say you have 0, 1, 0, 1. This can also be the valid string in this language. 0, 0, 1, 0, 1, 1, 1. Okay, and then you can have 0. So how many zeros? 1, 2, 3, 4, and you have 4 number of ones. This is also a valid string. 0, 0, 1, 1. This is also a valid string, same number of 0 and same number of ones. So this kind of string is there in this language. So if you are given the language which has the same number of zeros and same number of ones, and somebody asks that, okay, can you prove or disprove? Prove or disprove whether the language L is regular. So you may ask that, okay, prove whether this language is regular or not. So how can you prove? These strings now all zeros may not comes at the beginning. Your zeros can be anywhere, but your condition is that you have the same number of zeros and same number of ones. So somebody, you know that once you are going to select the string x, then you have to ensure that the length of x is at least n. So in your selection, you can include the zeros and ones and ensure that the length is at least n. So x can be taken in many different ways. You can have here 0 1 0 1, then so you can have any 0 0 or 1, like you have, if you have the n, you can say that some zeros and some n here you can have. So you can have some various ways to select. So like you have one way to select is that you can take 0 and 1 n. This is one way. Other strings in you may not have, because you know that all zeros and all ones, this is also a valid string, same number of 0 and same number of ones. Other strings can be x may contains some, say, some zeros, then 1, some zeros, again 1, and you can have to ensure like this. So you can say that this may have the length, some length, then you can have some length of the string. So total length of this string can be at least n. So you have to say some including 0 and how many zeros you have included, say I, how many and how many number of ones you have included, some I, j, like this. Here how many zeros, so some you have involved some number of i's here, some ones, some this, and finally total number of elements in this string more must be more than or equal to n. So now see, selection of this kind of string is more complicated for achieving the contradiction. So why you go for such kind of complicated string to be selected? Since this language says that, say, x contains same number of a's and same number of b's, means same number of zeros and same number of ones. So take the simplest string like we have selected the earlier. So this is the simplest string you can take, which clearly shows that the length of x is more than n, and same number of zeros and same number of ones, and this is clearly in the language. And once you have this thing, then you can use the same philosophy here we have already done to prove that, to achieve some kind of contradiction. So again, you have taken 0 and 1 and uv will be some zeros, v can be some zeros, j greater than 0. Then all such strings, if it is in the language, then uv mw must also be in the language. But you have seen that for m is equal to 1 only, this is in the language, same number of 0 and same number of 1. But for other cases, it is not in the language. So using this only, using this simplest string only, you have achieved the contradiction. So this is very important actually. This actually I want to tell you that you don't go for some complicated string. You take only simplest string for which you can easily come to know that the length of this string is at least n, and this is in the language, and for that string you can easily come to know what uv and w can be, and you can achieve the contradiction. And this is the way you can apply the pumping lemma for the regular language. Okay, so this is the property we have seen again for the case of the regular languages, and if the language is regular, then pumping lemma must hold. So if L is regular, so you have, if L is a regular language, then then it must hold the pumping lemma. So this is we have seen. So this is one property of the regular language we have seen. So if L is regular, then you have to say that it must hold the property of pumping lemma and it must satisfy the pumping lemma. So earlier we have seen the number of regular languages. You can take any language which is regular and try to find out whether you can achieve some contradiction. You will not find any contradiction, and you will say that all u, v, m, w belongs to the language for every m greater than or equal to 0. If L is regular, then you will achieve for every greater than or equal to 0, you will achieve that, okay, all such strings are also in the language. So at home, actually, you practice for this. Take some language which is regular, take some string whose length is at least n, and then you will come to know that you will not find any such strings for which you will say that, okay, this is the contradiction. If the language is regular, then it will satisfy the property of your pumping lemma.